who is the Hugh Rogers Endowed Chair Associate Professor. Does that mean they support you with that? Okay, whenever you see this term endowed, you may not know what that means as an undergraduate. That means somebody, Hughes and Rogers, or this particular person has put up money to help support his research efforts. He's also the principal investigator on a $20 million agricultural grant, which he just received, I think, in the last couple of years. And so, famous guy. And he's going to talk about human in the loop for learning for anomaly detection. So you can't get away from humans, hopefully. That won't happen anytime soon. You know, when you have an AI conference, you'd be all AI and we'd be AI and we'd be interactive. We could save us a lot of time. That will never happen. Okay. Go ahead. Yeah.
Thank you very much for the nice introduction. Sorry, my voice is not at the best today. I hope you can bear with me. But I'll try to make sure, you at least get the main message across, even if you are not an expert in machine learning or anomaly detection. So the title of today's talk is Human in the Loop Learning for Anomaly Detection. This is actually a paper that is published fresh off the press, like a couple of weeks back at one of the top AI journals. And this is a work done by my former PhD student, Rakibul Islam, who is a research scientist at Meta Research now, where he uses some of these things to fight bullying and nasty comments on Facebook and Instagram. And Shubhamoy Das, who was my postdoc. So, so the punchline for this particular talk and the broader theme here is that I personally, I have been working in AI for about 18 years now. I don't believe all solutions will be completely automated, will be taken care by AI or machine learning systems. I envision, and a lot of people envision, that there will be a symbiotic relationship between humans and the AI and machine learning systems, where they both will work together as a team to get a broader problem solved. And that's actually the view I take for this particular case of anomaly detection. So let me try to introduce some motivating applications for anomaly detection. So credit card fraud detection is actually one anomalous anomaly detection problem, right? So whenever you go to a foreign country, you make a purchase, you would probably get a text message on your phone or on your email saying, do you approve this, right? From Chase or other companies, right? So they have certain rules that they have written that, when something happens, that would be triggered and you would be alerted that something anomalous happened. So the question is, how can we automatically identify such unusual transactions? I would be annoyed if I keep repeating getting the same thing, like, okay, I'm trying to buy, let's say, jewelry for my wife for my wedding anniversary, and it's probably more than $2,000, and I have never spent more than $2,000 on my credit card. And I just approve that, well, this is me actually, through my mobile phone, and still I keep getting messages, then I would get annoyed, right? So what we want is that we don't want a lot of false alarms here, something that is actually usual, but the system says it's unusual, right? Because it's, first of all, there is a human aspect to it, and we are wasting the human's effort in this case. So we want to somehow avoid such situations. Another application is this ICU patient monitoring. So we all know, especially with COVID and stuff in general, we have less resources, especially from a medical side, than the amount of people they need to serve, right? So as much as possible, if we have some automated tools that will allow us to use our resources in a better way, that would actually help. So for example, you could think about a patient monitoring system, and only when something unusual happens, a call would go to a human analyst or an operator who would come and then look at the patient, right? But again, every time the nurse or the human gets actually these kind of alarms, and a lot of them are actually false alarms, then we are again wasting the human's effort in this case, right? Which is the most important priority for us. So how can we reduce such false alarms and but still identify such anomalous situation? And the third motivating application is this mobile malware, right? So the anti-malware industry, it's a huge industry. Microsoft has some component, McAfee has actually some component. And as you can see on the right side, I'm showing you the number of malware samples that has increased over years, and this is only until 2017. So there is uh, it's like a cat and mouse game where the people, the attackers want to create more and more malware, and the good guys want to create these malware detectors so they can actually save you, right? And each of them wants to be ahead of each other, right? So the question basically is that how can we identify such malware apps? So the problem, now that I motivated you with few applications, the abstract computation problem is we have a bunch of inputs and we don't know whether they are anomalous or normal. And we want a computer algorithm or a software to look at that data and tell us which ones are anomalous and which ones are normal. So the anomalous points are red colored and the nominal points are green colored. And ahead, we don't know anything about the data. So the main challenges in solving this simple problem is that it's like finding needles in a haystack. Because the number of anomalies are way smaller compared to the number of nominals. So it's typically a knowledge discovery task that involves humans because you need some guidance from the humans to identify those red dots out there. And as I have been trying to motivate through the three applications, the higher the false positive rate, you're wasting more and more human analyst effort who is in the loop here, right? So somehow what we are trying to go to do is how can we actually improve these anomaly detection systems based on the feedback from the humans so that the false positive rate would go down as the user uses the system more and more and provides feedback. So the prior work on anomaly detection, much of the methods are completely unsupervised, right? So which means that they don't get any feedback on what does an anomaly mean or what does a normal data point mean. And most of them are some sort of statistical methods and they make certain assumptions about what they consider as anomaly. Okay. And one of the state of the art methods in unsupervised anomaly detection is what is called isolation forest. And that would be the focus of today's talk. But the methods are more generally applicable to a broader class of problems. So let's first talk about why unsupervised methods may not work in general, right? So as I mentioned, every method makes some assumptions about what is nominal and what is anomaly. And when those assumptions are violated, of course, you are going to get wrong answers. Okay. And sometimes the nature and the type of anomalies are not known beforehand. It's almost like unknown unknown. So unless you see them, you don't know that you don't know them. Right? How do you figure out those? And only a subset of the identified anomalies are relevant for the real world task. For example, imagine there are a bunch of anomalies of different types. And if the system keeps telling you about an anomalous point about a single type, you are missing all the other anomalies of a different type. So the bottom line here again, I want to highlight is that if you are producing lots of false alarms, then you are wasting the human analyst effort who is in the loop. So the main question we are interested in answering is how can we use a human analyst efficiently along with these algorithms? So combining the best of both worlds to improve the anomaly detection rate and reduce the false positive rate, right? So the high level idea here is that the algorithm will query this human analyst by saying, well, here is a point. Do you think it is a nominal or an anomaly? And then use that feedback to update its understanding about what is nominal and what is anomaly. And then it repeats the process again. Again, it asks the expert, and the expert says it's a nominal because it gave a green color. And then that goes, and the model gets updated, and you have a new data point, and so on and so forth. Right? So what this interaction is telling you is that the human is providing some feedback about which data points are normal and which data points are anomalous. And the overall name of the game here is that we want to minimize the number of queries we ask this expert because expert's time is valuable before we discover all the anomalies that are there in the input data set. That's the name of the game that we are going to play today. So before we get to the algorithm, as I mentioned, this isolation forest is the state-of-the-art unsupervised anomaly detection algorithm. And isolation forest basically comprises of a bunch of trees. So it's an ensemble model where if you have one model, it tells you anomaly, it might not be accurate, but when you combine and vote across many trees, you will get a much better accurate prediction. So the key idea in isolation tree is that the anomalies can be easily isolated from nominals, and the degree of anomaly is inversely proportional to depth. So what it does is it picks up some feature or attribute of the input randomly, and it creates a split condition, right? Both a random feature and a random split to decide whether the data point would go on to the left side or to the right side. And it repeats the process recursively. And if the points lie in the deeper leaves, that means that they are more normal. And if the points lie in shallower leaves, that basically means that the points are anomalous. So anomalous points are easy to separate out. And here I'm showing you every leaf corresponds to a subspace. And these are all the partition subspaces. And now on the right hand side, I showed you the depth colored subspaces. And as you can see, the node score here is a function of path length, which basically means that all the nominal points will have higher path length because they are actually at higher depths compared to the anomalous ones, which are at the lower depth. Now, as I mentioned, a forest is nothing but a bunch of trees. So you take the same isolation tree, right? And then combine, have multiple times, repeat the same process, and you have multiple isolation trees. And the main thing here is that it assigns uniform weights for subspace scores. So what it does is that every point goes to some subspace through each tree. And it assigns uniform weights for all of them and just combines them to give basically what is the overall anomaly score for a particular point. Let's say many of the trees says that a particular input is actually at a lower depth. That means that this is more likely going to be an anomaly. Whereas many of the trees says that this point is actually at lower depth, right? Which means that this point is more likely to be a nominal point. So, like I mentioned, this is what it does. So that is the tree representation. And when you have 100 trees combined, this is how the partition looks like. And when you look at this contour plot, the middle part is actually the normal nominal points. And as you go away, these red points corresponds to, these red areas corresponds to anomalous regions of varying degree. And as you can see, the decision boundaries for nominal versus anomaly is much more complex and accurate in the context of the forest compared to the trees, right? So that's the point that we are trying to make. So as I mentioned, the isolation forest, what it does is it takes an input X and maps it into an m-dimensional vector, right? Remember, if you have m trees, each of the point will go to one of the leaf in that particular tree, right? And all these subspaces are actually equally weighted. So it doesn't have any dynamic weights. And that's actually one of the problems. So when it tries to compute the score, what it does is it just combines the scores of this input that is given by the different trees, which is the path length, and then rank all of these points according to these scores, right? And then pick the top tau candidates as anomalies. So for example, if you have 1,000 points, you score all of them according to the scores that the isolation forest is saying, and then you sort them and you pick the top tau candidates as anomalies. But the main issue is that the accuracy or the number of anomalies that you would find in this top tau ranked anomalies depends on the weights of the model. If you're assigning everything uniformly, right, then the anomaly detection rate would be very low. So the question is, how can we learn the right weights for each of these subspaces so that our anomaly detection rate starts going up? And that's what we are going to do here. As I mentioned, this is an iterative loop where the algorithm presents one input to the human analyst and would potentially provide some sort of an interpretation also, right? So for example, the system now thinks this is potentially an anomaly because the credit score of the person is low and the person is not employed, right? So this gives the context to the human analyst that why the anomaly detection system thinks this is an anomaly. And then the human analyst actually looks at the data and then figures out whether this is a real anomaly or a nominal. And then that gets added to the labeled data set. And that labeled data is used to update the weights. So there are two questions here. The first question is, which queries the anomaly detection system should present to the human analyst? Because remember, our human analyst's time is actually very, very crucial. So we want to minimize the number of queries that we are asking. So we have to be really careful and intelligent about which queries we are asking the human, right? And it turns out that greedily asking, picking the point which has the highest score to be asked for a query actually does really, really well. And I'm not going to go into the details, but the paper has the details where we theoretically show why that is the case. Okay, so all you do is that according to your current weights, you sort all the unlabeled examples and pick the one that has the highest score. And then you present that to the human analyst, and the human analyst provides the feedback, and you re-rank them again because your scoring function or the ranking function has changed based on the feedback, and you repeat the process. Right? So the only thing that is changing is that how many labeled and unlabeled examples are there in your set now. So as I mentioned, one thing is that, let's say repeatedly I found one type of anomaly, like for example, in the credit card fraud detection, whenever you are in a different country or a place than where you used to work on a normal day, right? Whenever a transaction comes outside the place of where you live, then potentially it's an anomalous thing, right? But if I keep asking the same kind of inputs, even if I know that is actually an anomaly, I am not discovering anything new. So if I want to discover different types of anomalies, then my query strategy should change. That the goal is I want to discover diverse types of anomalies, right? Maybe one type of anomaly is that maybe if your transaction amount is way higher than anything else that you have bought before, right? So that's another type of anomaly. So the nice thing about these trees is that they have some inherent structure that we can actually exploit to ask these diverse queries, right? So what we do here is we try to select some subspaces that covers many of the nominals or anomalies that we have identified. So if you see here on the left side, there are many subspaces And here we try to find through a set covering algorithm a kind of subspace that covers many of the nominals or anomalies that we have actually covered. And what the diverse selection does is that instead of asking all the queries from basically a same area, it will try to diversify by asking queries from these different subspaces that we have identified as part of our set covering algorithm. So, yeah. So then the second question is, now we know that how we are asking queries to the human expert. But now once we got the feedback from the human expert, how will we update our models? Remember, what is our label data? The label data is that we have a bunch of nominals and a bunch of anomalies that were labeled by the human expert. And for unlabeled examples, I don't know anything about it. So what I want to do is, I want to find the weights of the ranking function such that all the anomalies are ranked higher than the nominals, because that is all the information that you have. So you tune the weights of these models such that until you have satisfied this constraint that all the anomalies are ranked higher than the nominals. So, it's a simple online learning update that's pretty common in learning to rank literature. That's what we do. So here I'm trying to show you the illustration. So here are your current weights. Here is the top tau quantile, and here are your anomalies, and the nominals are here. And now this person has labeled this point as nominal. And then now what we are trying to do is that we are trying to learn the new weights such that that green point goes actually below the threshold of tau. And again, we get the point, and let's say that is actually an anomaly. So we want that point to be ranked in this top place as opposed to the bottom. And then we repeat it. So we have done a bunch of experiments, and I'll show you some results. So one question that is interesting in this human in the loop is that we're asking how many questions I have asked to the human, and out of them, what fraction were truly anomalous? A good querying strategy means that a large fraction of your queries resulted in anomalies, because that is what you are after discovering. Remember, you are trying to find needles in the haystack. By every time you're querying, you find more and more needles. That means that your hit rate is high. So as you can see, the algorithms that are doing well will actually be at the top. And as you can see, these are the ones that are being trained using the feedback as opposed to no feedback, right? So this unsupervised baseline, for example, it is very clear here. You can see that the human in the loop ones are actually doing better than the unsupervised version. And only with a small amount of feedback, you are able to discover a large fraction of the anomalies. The last part of the talk is on streaming anomaly detection. So far what we assume is that all the data is given to you ahead, and then you are trying to find anomalies. In real world, it doesn't work like that, right? Maybe a bunch of tweets are coming. Maybe a bunch of social media streams are coming. Maybe a bunch of communication data is coming through a network, and you need to find on the fly whether something is nominal or anomalous. And we will try to see how we can attack this problem using some of the principles that we have seen. So this is how it looks like. So we are looking at time axis, and the data is coming across time. So at T1, this data showed up. At T2, this data showed up. At T3, this data showed up. And the main thing is that whenever the data is coming in a stream, you need to identify whether the data distribution has changed or not, right? Only if the data distribution has changed, you have some reason to believe that you need to update your anomaly detectors or its weights, right? So if there is a concept drift, then the second question is, how do you update the model? Your model is stale. Maybe some of your trees are stale. Maybe some of your weights are stale. right? And the third thing, you say, well, one of the things that actually I can do is I can convert the streaming problem to a static problem. In a sense that I store all the data that is coming over time and store it and run the previous algorithm that we talked about, right? Now imagine if you are getting data at the rate of, let's say, 1 gigabits per second. And if you keep storing all that data, soon you would be running out of memory, right? So that solution definitely won't work in a lot of practical applications where the data is coming at a very fast rate and you cannot store them on your disk. So this is the idea we'll talk about. So we have a bunch of trees at time t1 based on all the data that we have seen, and we have the current weights. And then new data comes, and then we have some new trees added or deleted, right? And then we ask some feedback, and then another time new data comes. Again, we have some new trees and so on. So the question basically becomes is that do we need to change our model, which means any of the trees should be replaced? What fraction, right? So we have a drift detection algorithm. So what it does is you look at all your previous data, right? And you map it into some non-parametric distribution, right? And then you have your new data, and again you basically form a similar distribution, and then you compute the distance between these two distributions, right? When you have two distributions, one good way to learn the distance between the distributions is what is called KL divergence, right? So you don't have to know the name, but at this point, all you have to know is that if the distance is larger, which means that the new data has a lot more information than the ones that you have seen. And you should do definitely something about it. So here I'm showing you that the data drift detection results. And here, the two cases, there was not much drift that was observed. Whereas if you see the last case, the right-hand side, there is a lot of drift actually here. And this is the case where we need to update our model. So there are two cases, right? So when there is only a minor concept drift, all we have to do is that we just retrain based on the new data. But if we have a major concept drift, which means that the KL divergence distance is actually pretty high, then you replace a fraction of the old trees and you then include new trees based on the new data that you have got, and then again initialize them with the uniform weights and keep updating based on the feedback from the expert. So one natural question you would be interested in is that, well, when you know the entire data and then you're trying to figure out basically these anomalies to the human in the loop, that's like the best case scenario. There is no information lost. You know all the data, right? But when the data is coming in a stream, you have some information loss. You don't know what future is, right? You are bound to perform suboptimally compared to the case when you know the entire data, right? So the natural question here we are interested in is that when the data is coming in a stream versus when we have the batch data, what is the gap, the performance gap between these two algorithms? And the smaller, the better, right? So here you can see that the highlight batch is consistently the best performer. And as you mentioned, it has this additional advantage of knowing all the data, so it will do the right thing. In the streaming case, we don't have the luxury because we don't know what the future is, right? But the performance of the streaming algorithm is pretty close to the batch one. We cannot beat the batch one, of course, because it has the extra advantage of knowing the hindsight, right? And here are some results of replacing the trees like 10% or 20%. And in general, what we have seen in our experiments is that when we have a high drift, then replacing with 20% of the trees actually works reasonably well across. So to summarize, there are 2 points that I made. I made that anomaly detection is a hard problem because it's almost like finding needles in a haystack. And unsupervised approaches may not always work well because they don't know enough about what are considered anomalies that are relevant in a particular domain. And then I said, isolation forest is the state of the art unsupervised approach. So, but the problem is that it will result in a high false positive rate, which actually wastes a lot of the human efforts, analyst effort. So the two things that we talked about was how can we build on the strengths of isolation forest and try to improve it further to reduce the false positive rate, right? So we said we will ask the human some queries and human will give some feedback about nominal or anomaly, and we will use that information to configure the anomaly detector's weights or parameters such that we discover more and more anomalies. And we talked about two scenarios. One, where we have this batch data, all the data is sitting on a disk, basically, there's no other data. And the second case was the streaming data, which is the data is coming in a stream. And we saw in the experimental results that the human in the loop version finds more anomalies compared to no feedback version. And then the streaming algorithm works pretty close to the batch version. So that's the end of my talk, and I'm happy to take questions. I don't know how I was doing my time.
Yeah, we're great on time. We got a couple questions.
Okay, good. Yeah.
So for part of our CySER project, James and I did some work on like the product fraud detection.
Uh-huh.
I guess kind of a question for James, but will this also be kind of related, sort of like a different method?
Didn't quite do that last part.
I said, would this like, what you talked about be kind of related to what we did with credit card fraud or?
Yeah, it's, yeah, very much related. So we work with, decision trees and random forests. We use isolation trees and isolation forests. So maybe you could talk about the difference there.
Yeah, so the isolation forest, the way it works is that it doesn't assume any labels, right? When you have labels, right, so what you can do is you can actually throw away the labels, run the isolation forest algorithm, get the tree, and now then bring the labels, and then you tune the weights of those things, and you can compare apples to apples, right?
So what we were doing was supervised, because we have labels on all the
Yeah.
data, so this would be a different scenario for that.
Exactly. Yeah. Any other questions?
What does it look like on, so for the human in the loop, are they sitting at a computer getting asked, hundreds of questions an hour, or is there, so how does that, what's the practical side of that?
The practical side of things, I mean, of course, it's actually about the time, right? So we cannot ask too many questions actually, right? We have to take into account how much time actually the human can actually spend on a single query, and then we have to time accordingly. Or we could actually do some batch processing where we could say, well, instead of a single query, I will give you a bunch of queries. Now you process at your pace, and then I will process again. So we haven't really deployed anything in like real world to know about any of these, but it can be configured according to the needs basically. It depends on the rate at which the data is coming, for example, right? In the tweets case, for example, I mean, I cannot imagine anybody would be able to process all the tweets, for example, right? So I think we have to be mindful of it. Yeah. But that's a good question, practical question. Yeah, I think one thing that I would actually encourage some of you if you're looking at projects, how you can use some of these anomaly detection algorithms or the human in the loop algorithms to overcome bullying, for example, or some kind of a misinformation, right? All such, or some kind of abuse, you have a lot of those things in the social media, right? So these algorithms could be super useful, really, to address some of those issues. So if you guys are looking for projects, I think those are great applications for this.
Anyone have, I know the students I work with have a little bit of background on machine learning now, it's a little bit, but anyone here? Yeah, I know we have an undergraduate. Permanent. To provide research. Me and Emily, we had, like at the tail end. Okay. What kind of model did you use? What did you do with it?
We were seeing it, we were using label data, but it was, we were trying to predict if something was Trojan.
Okay.
And using that to compare, the predicted and what actually.
Yeah, I think the malware also there is a very interesting problem. People use machine learning all the time to detect malware versus the normal apps. But over time, the behavior of the malware apps actually change, right? So a real evaluation would be if you have trained a machine learning classifier on like say 2024, all the data. Now 2026 comes new apps. How could this generalize to those scenarios? I think that's actually an open problem. I don't think this is a good solution right now.
That's something Dr. Hyden Kai is working on.
Yes,
We'll get to
yes,
hear from him
Yes,
next week, tomorrow.
yes. Any other questions? If you don't have any questions right now, I mean, feel free to email me if you have any other follow-up questions. I'm happy to answer.
Oh, the paper you sent me, that is up on the CySER website on the workshop, so.
Yeah,
Dr. Gopal, I don't know if you want to just mention that paper, they can go there and read it.
yeah, so we have on my website also, it is there, it's publicly available, it's not like a paywall, it's all on archive. And even the code for this particular thing is publicly available, so you can actually use it as needed. And if you have any questions, you can drop us an email. Thank you very much. Yeah, thank you.